Hello and welcome back to Calculus 1, section 2.6 on continuity. Now, before we go into the definitions and theorems and all of these kind of things, continuity is a little bit more than just having a line without any breaks in it. When the line does have breaks, it's clearly discontinuous. But sometimes continuous functions have to be also drawn with non-continuous pieces, which is weird. And if you really dig deep into mathematics, take advanced courses, advanced calculus, and so on, you will see a function that is continuous function, but you cannot draw that function in one strike like this. You actually have to draw pieces back and forth, but they all lock in and the function is continuous. But for our case, right, when you start in Calc 1 and you're learning basic concepts in elementary course, you start with some function f of x and you say, you know what, this function is continuous, this function is has no breaks on its domain, right? There is no break in the domain. It's one full continuous line. Now we have a global continuity, piecewise continuity. You can take a look at the entire domain and claim continuity, or you can just take a look at the piece of the domain and claim continuity. And we'll talk about those as well. Now, what I want to say here, and I'm going to pick one point here. I'm going to say that we have a function a. I'll put this to be the answer for it, which will be L, and let's see continuity. At the point x equals a. So function is continuous at a if these three conditions are satisfied. Condition number one, f of a must exist. 2, limit of f of x must exist as x goes to a. And third is that the limit of f of x needs to be equal to f of a, which is our L over there. So this technically says 1 is equal to 2. That's what it says. So these are your three rules. And when you are checking for continuity at the point, you have to check all of these rules, all three rules. And if these three rules all fit, then you have continuity at A. And then we define the global continuity by saying if the function is continuous at all points, right? If the function is continuous at all points, then the function is globally continuous. So that's another definition that we say. So global continuity if f of x is continuous at every point in its domain, then we say f of x is globally continuous. Continuous. All right. So I can have a function f of x equals x squared minus 2. And I want to check continuity at x equals to 6. I go like this. How much is f of 6? It is 6 squared minus 2, that's 34. Then I check for the limit x goes to 6 of x squared minus 2. Now, this is one of those basic functions. We don't need any special witchcraft for this, algebra or anything like that. We can just plug in. So we again get 34. So we say exists. And now rule 3, we see that 34 equals 34. And that checks out as well. So because all 3 check out, and you have to do all 3 every time, right? You can't just look and say, yeah, it's good, right? You calculate the function value, you take a look if the limit exists, and then if those two numbers are the same, that number 3 there also is the part of the definition. And now we can claim, right, that, so we say x squared minus 6 is continuous at x equals 6. And this is problem solved. This problem is done now in for your Calc 1, right, for continuity. You can try and say f of x equals 1 over x squared, x equals 0, continuous or not. You go, all right, how much is f of 0? Does not exist. Well done. As soon as one of these 3 conditions, as soon as one of them fails, immediately continuity at the point is lost. So it's not going to win 2-1, right? It can only have all 3.
Sorry, could you repeat that again?
Repeat what?
The
It has
last
to
part,
have,
as soon
all
as
3. Yeah, as soon as one fails, as soon as one of the 3 rules fails, function is immediately discontinuous at that point. So as soon as one fails, and that's actually the next thing that I'm going to write, right? So if any of the 3 fails, f of x is discontinuous at x equals a. So only if all 3 pass, you have continuity. If one of them fails, any one of them, it's immediately discontinuous. And now we can actually see how all of these 3 affect the graph. So I can have the situation where I have a function and this point at A is dislocated. I can have a function where the function is all happy and then there is a jump like this at A. I can have a function that goes and then just a hole going that way, right? So in each case, this is my f of x, a little bit different versions of f of x. And now I hope you guys see what's happening. What do you think, which rule fails? Let's say on the middle picture, which rule fails? Rule number 1, Do we have f of a?
Yep.
Yes. So that one passes, right? Because f of a is right here. How about 2? How about the limit?
Yes.
Does
Sorry, I'm
not
looking at graph 1.
It's that's the one that fails. Because approaching from the left, you are getting this value. Approaching from the right, remember Romeo and Juliet? We get this value. They are not the same y value, and by that definition, in the first theorem we learned, when the two side limits do not match, they have different y values, then the overall limit does not exist. So it failed as the second rule. Now, you can see, right? Looking at the graph, you can see that it's discontinuous because there is this gap, right, in between. And this would be your vertical drop, for instance. So it's clearly discontinuous. You do not want to have a road that has this kind of sideways continuity, right? Where the car goes, then there is a 10-foot drop, and then you go, right? How about the first picture, let's say? Do we have f of a?
Yep.
Yes, right here, f of a. So it passes that one. How about limit? Do I have limit?
Also yes.
Yes, very good. When I approach from the left, when I approach from the right, I always get this value here, L. So I do have that one as well. How about the third rule?
Nope.
Nope, right? So we see that for the third rule over here, f of a is not the same as L, because L is, right, all the way up there, and f of a is down there. So there is no, they're not the same. So the function is discontinuous. And that's the idea. Remember the bridge? That's that one. Where is the piece of the bridge that it's missing? It's in the water, right here, right? So the bridge is discontinuous. At which point, I guess, they can percentually charge instead of $20, they can maybe put 18, right? Because the section is missing. But the rest of the bridge is okay, I guess. And how about the last picture?
There's no f of a.
Beautiful. No f of a. So since there is no f of a, we have discontinuity fails, right, with the first rule. So now you see that all three of these, right, you need to know all three rules. You need to check all three rules because for a given function, any one of them might fail. And if it fails, obviously, the function is discontinuous. Now I want to jump into the homework here and pick one of these piecewise functions. Usually, those are the ones that you don't like. They want, in problem 22, they want to check function f of x given as a piecewise function, x squared minus 4x plus 3 divided by x minus 3 if x is different than 3, and 2 if x is 3. So they are looking for continuity, and obviously they will be looking for continuity at 3 because nothing else is nothing else is interesting, right? You can see that 3 minus 3 in the denominator would make a 0, so obviously that would be interesting thing. Now, before you jump to conclusion that it's discontinuous, I need you to make this clear in your head. The top function part, right, is going to make something like this. And the bottom is going to make something like this. Now, in some cases, they will be disjoint like this. And in that case, it's discontinuity. But if this black dot happens to be plugged right where it should be, then the function is continuous. So you cannot give an answer by looking at the form of the question, because all I need to do is to adjust the height of this value. Number 2 means y equals 2 height. But I can put 3, I can put 2.1, I can put e, I can put pi squared, right? I can make sure that it fits this hole perfectly, in which case it's continuous function. And if it doesn't fit the hole, then it's discontinuous. So you should not be drawing the graph here. You should be computing the 3 rules and then making your decision on, yeah, I passed all 3 rules, or nope, I failed the rule, therefore discontinuous. So we start with f of 3. F of 3 is 2, exists, right? Because when x is equal to 3, y is equal to 2. That's the way you read your piecewise function. So the first line is fine. Now we go with the second line. Limit of x squared minus 4x plus 3 over x minus 3 as x goes to 3. Well, if I try plug and pray method, it's not going to work, because 3 minus 3 is 0 in denominator, which means that we have to use algebra to solve this problem. That means that I have to break this problem into the left limit and approach from the left. So x approaches 3 minus. And then the blue one, limit x goes to 3 plus over here. If those two numbers are the same, then the overall limit exists and we say pass. If these numbers don't agree, then we fail the second, because the limit does not exist, fails the second rule. So let's solve these two limits. We have to factor, right? So we get x minus 3, x minus 1 over x minus 3. These guys cancel. And when I put 3, I get 2. Same calculation happens here from the approach on the other side, which we still have to check, and we get 2. So the overall limit here is 2. It passes the second rule as well. The third rule is 2 equals to 2. It passes that one, and we say yay, or yes. F of x is continuous at x equals 3. Because it passed all 3. Now, can I give you this same problem and just change this into a 5? I can. So in that case, this would be 5. This would still stay 2. But then 5 is not equal to 2, and the problem becomes discontinuous. So it's very easy to make them continuous and to make them discontinuous. You cannot memorize the example and say, oh yeah, it's always. No, 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 no. Right? You have to compute from scratch. And the problem can go either way. And that's why we always compute. So in this case, because they all lined up to be 2, right? The function value was 2. The limit left and right gave us the overall limit of 2. So everything lined up, and we have 2 everywhere. So that's it. That's your continuity at the point. So now, how many points do we have in a polynomial function? How many do we have in exponential function? Right? How many points do we have? We have infinitely many points. So now you have to sit there, right, and compute forever, right? No. Right? No. We learn a theorem for global continuity, and we remember which functions are globally continuous on their domain. So the next 2 theorems will be used in Calc2, Calc3, differential equations. So if you learn these only for the test, you will have to relearn them for chapters worth of stuff later on in your Calc2 and so on. And I'll show you briefly what I mean. But let's go first and take the list here. Following functions are globally continuous polynomials, meaning p of x equals a0 plus a1x plus a2x squared plus ... plus anx to the n. This includes constant function like y equal 4, always continuous across the board. It includes y equal mx plus b linear, and a quadratic, and a cubic, and so on. So all of the polynomials are in there, and they're all continuous. You don't have to worry about vertical asymptotes and so on. Vertical asymptotes create discontinuities and other things as well. But number 2, exponential function, y equal, let's put a to the x or b to the x, whatever. 3, logarithmic function, y equals log base a of x. 4, radical function, y equals square root of x. 5, we have sine x and cosine x only. Remember that the tangent has the vertical asymptote. So, and all of them, all the other 4 have all vertical asymptotes. All of them have vertical asymptotes. Therefore, only sine and cosine are continuous on their entire domain. Now, the others, this is a little bit, the book was a little bit vague about it. They listed the trig functions, but we are going to talk about piecewise continuity, where pieces are continuous, and then you say the principal period is from, for tangent is negative power 2 to power 2, and then it's continuous. So we'll deal with that. All right, so this is list of functions that you will run into as you do. Now you will learn hyperbolic functions and some other things as you go on, but right now these are the functions that you should memorize in terms of continuity. And then there is also this one. Let's go purple on this one. This one says that combinations and composition of continuous functions are continuous. So combinations and compositions of continuous functions gives a continuous function. This is a huge deal. This one is very important. That's your f plus g, f minus g, f times g, f divided by g provided g is not 0, f squared, and then what else? And then f of g and g of f, and those tend to be very, very important. So these are your function compositions, combinations, and if I have a function y equal, or f of x, let's go f of x, equal to sine squared of square root of x, of, let's go with e to the 3x. Continuous? Nick, what would you do? You actually use this and you write a paragraph answer that the function is continuous. Right? So you start with 3x is polynomial, hence continuous. Then you call, right? So this sentence was calling on this. So you used this theorem, this part, because 3x is a linear polynomial, right? All polynomials are continuous. Therefore, you made the claim that 3x is continuous because it belongs in this black box, what you see right now on the screen. So 3x is continuous. Then what you do? You say, now you're going to call on purple, because this function technically is sine e to the 3x everything squared, right? That square can be written on sine, or you can put parentheses on everything and then square it. So now you call on the purple and you say that e to the 3x is continuous because, and I'll just say purple. You actually say composition of two continuous functions is continuous. And then sine of e to the 3x, that's another composition, is continuous because purple. Purple statement, purple theorem, not word purple. Do not write purple on a test, all right? Or in Calc2 exam, do not write purple, because whoever you take Calc2 will not know what was purple, all right? So the purple statement is function composition of two continuous functions gives continuous function, or is continuous function, whatever. And finally, right, when you plug in sine of e to the 3x into this, that's another function composition. So is continuous because purple. So you would write purple statement 3 times here. And as I said, this is used. I'm going to jump into Calc2. Doesn't matter which one I pick. Let's try Calc2 from 2018. Doesn't matter. And we're going to go into integral test, for instance. Let's see. Look at this. To do the integral test, you need to show that something is continuous on A and B. It's a condition that you have to check to do the problem. So, is it continuous? Yes, it is, because it's easy function. There you go. Is this continuous? Here is the answer. Yes, because both 1 and x are continuous and their quotient is continuous because the denominator is not 0, blah, 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 blah. Right? So we are using this to solve our problems. And you will be using these theorems later on. So the more you learn now, the less you will have to relearn and review later. Okay, so that's that. What else do I need? So that's the global continuity and all of those beautiful things. Let's now talk about piecewise continuity, which is not discussed in the book to the extent they should, so that you can actually do the homework nicely and then do your other courses and after this one. So piecewise continuity. Let's all immediately agree y equal 1 over x is discontinuous at 0. I don't think I need to talk about that, right? We all see that the function is broken at 0. So discontinuous at x equals 0. Therefore, function is discontinuous globally. It's discontinuous function. But if you paid attention earlier in the example that I showed, right, we had, well, how about, is it continuous on the interval from 2 to infinity, 1 to infinity? And in that case, yes, it is, because you don't care about the rest of the function. So this function is discontinuous, and we do not need to debate that. I mean, there's no debate in this class. There is only, right, there are theorems, no debates. We do not need to discuss and explain that, because you see that you cannot continuously walk from this point to this point, because this shoots to infinity and then picks up on the other end and so on. So yeah, discontinuous. But if I look at the part of the domain, all of a sudden it's continuous. So if we look at, let's say, 1 to infinity, see, 1 to infinity is this one over here. And that one is continuous. It's a continuous piece. So piecewise continuity takes a look at the different pieces of the function, because sometimes you just need a piece of the function to work. You don't need the entire function to work. I mean, if you were not able to do this, we would not have electricity. We would not have any of the stuff work that is using electricity, and that includes AC and DC. There will be no batteries. There will be no outlets with AC power. There would just be nothing. We would still be banging 2 rocks to make fire, like 500 years ago. Granted that electricity is only 200 years old, but not even. Not even. But yeah, you have to think about that, because this is the graph that governs the Ohm's law, right? And the Ohm's law says that the current is equal to the voltage over resistance. And the graph for that would be this, like that, where this is your resistance and this is your current. So when you plug something, it has the value right there, or right there, or right there. When you put infinite resistance, there is no current, and in that case, light bulb, let's say, doesn't work. Well, that's called flipping a switch, because in order for current to go through a circuit, if you have a switch, and let's say you put the battery, and you have a light bulb, like that, when you close the switch, the circuit is closed, and the light lights up. This could be LED or whatever. When you open the switch, the resistance between the 2 points becomes infinite. And because the resistance is infinite, this is your limit at infinity, your current is 0 and the light is not on. And what is current? Current is movement of electrons through the medium wire. Now, if your resistance is 0, meaning you short circuit, you get a little spark if it's a battery. You get a mini explosion if you short circuit the outlet. Then in that case, resistance is 0. When resistance is trying to be 0, current is trying to be infinity, right? And temperature is proportional to current, which means the temperature is trying to be infinity in that case, and you get a little mini explosion there, right? So now you maybe understand, when the batteries explode, when the it's a flaw in the design. But all of these things, guys, are used a lot. Your job now is to learn the boring part of it, of how to compute the meaningless expressions. But once you figure out how these plug into physics and how they plug into the actual coursework later on, when you start taking your 300, 400 level courses that actually mean something, you will find these equations, and your level of and your ability to understand those concepts will come from here. Because you would say, oh yeah, when my denominator goes to 0, then the result goes to infinity, and when my denominator goes to infinity, my result goes to 0. And I just explained that through a circuit, for instance, right? You can do that with the water pipe and water as well, and the little valve does the same thing exactly, right? So that's the continuity, the piecewise continuity. They are all right, working together. And there is this one more concept in this lecture, which is extremely important to understand equations and mathematics. We don't use it. We have computers and stuff, but it's kind of cool, and it can be used. I had a student in the past who programmed these things just because it's a lot of fun. You can write a code. I always encourage students to write the code. That's in some sense more important than anything else you learn in the whole program. The part is called intermediate value theorem, and it actually tells you, the existence of the equations and solutions to equations. All right, so it goes like this. Suppose f of x is continuous on some interval a, b, so piece, and L is a number strictly between f of a and f of b, then there exists at least one number, at least one number means could be more, at least one number C in open interval a, b, satisfying f of c equals L. It doesn't mean much, right, when it's just words without the picture. So if I am to draw a function f of x, and then I pick values a, c, and b, and take a look at their y values, f of a, L, and f of b, we see that if a is continuous, and we only care about this piece between a and b to be continuous, if that piece is continuous, and L is a number between a and b, which is what we have over here, so those are our conditions, then there exists a C which is in between a and b. Now, usually people go, oh, yeah, okay, so what's the big deal? Actually, this concept solves equations of all kinds forever, and it is the basic building block of everything we have ever built as a species. So that's how crazy important it is. We never use it, but it explains the possibility and ability of solving equations. All I need to do is to shift that this L hits the x-axis, and generally what you have is, if you're solving equation that is equal to a 0, you can use this method to solve it to whatever precision you want. Generally, calculator will give you 5, 8, 12 decimals. If you do this by hand for a couple of hours, you can come up with 20, 30 decimal precision, right? Better than a calculator. Now, obviously, you can program the computer to give you as many decimals as you want. I was learning to a computer, but you can also do it by hand. And just realize that these calculators and computers are with us for the last 50 years. I mean, they did a lot more, right, than what we think they did without the calculators and computers just 50 years ago. So when you think about this concept, now I'm going to move this function and let it cross over here. If I have some equation, let's say, I don't know, 3x squared minus 1 equal to 0, or 3x squared equals to 1, then you make it into 3x squared minus 1 equal to 0. If you keep picking values so that this keeps f of a or f of b to be negative and the other one to be positive, you are guaranteed to have the solution in between them. And if equation has a solution, that means it can be physically made, because we understand it in that case. So we put all of these things together and everything works out just fine. Now, there is calculation. If you're interested, you can try and hunt down one of my previous lectures when I spent 30 minutes calculating by hand to 3 or 4 decimal precision for, you know, whatever problem I picked. The goal is to keep plugging A and B into the equation, making sure that one is positive, one is negative at all times. I mean, the answer to f of A and f of B. And keep cutting it down, cutting it down, cutting it down until you get into decimals, and then tenths, and then hundreds and thousands, and as precise and, you know, as deep as you want to go, right? Given that you are prepared to spend hours of computing these things by hand. That's it. Hope you're not disappointed. Continuity. We start with the continuity at the point, and then we define with the 3 rules. Then we define global continuity. Then we give the theorems on which functions are globally continuous. Then we talk about combinations of those functions. We also understand the ways to break the continuity by making sure that one of the 3 rules is broken. And then at the end, right, we give some application to it. And then we talk about intermediate value theorem to find the intervals which will contain the solution of the equation. Now, the reason why this is in is because it uses continuity in its definition, right, in its theorem, because f of x is supposed to be continuous. And I know that I can apply that theorem here because this is a polynomial, and we said that polynomials are globally continuous, so I can use it to solve the problem. And we can find, right, root 3 or 3, root 3 divided by 3. So we can look for the answer between 0.5 and 1 and keep going that way. So that's it. We're going to take a short break, about 5 minutes, for YouTube to process the video. And when we come back, we'll have about 10 to 15 minutes of 2.7. So I will see you in about 5 minutes or so.